Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3d hybridization, and for this type of hybridization I'm taking the example of phosphorus pentachloride. So our today's example is phosphorus pentachloride to understand sp3d hybridization. That's PCl5. Before doing the hybridization, let's make the Lewis structure of the PCl5. So that's our phosphorus, chlorine, 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 and that's the last and the fifth chlorine. Now let's talk about the phosphorus. What's the atomic number of phosphorus? That's 15. So the configuration will be 2, 8, 5. That means phosphorus is having 5 electrons in its outermost shell. So let's mark the 5 electrons around the phosphorus. That's the first electron, second, third, fourth, and the fifth electron. Now let's talk about the chlorine. What's the atomic number of chlorine? That's 17. So configuration will be 2, 8, 7. That means chlorine is having 7 electrons in its outermost shell. So let's mark 7 electrons around all the chlorine atoms over here. So I'm talking about first chlorine. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the second chlorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Let's come to the third chlorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the fourth chlorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Let's come to the fifth chlorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Now all the chlorine atoms will make 1-1 bond with phosphorus. So that's the first bond of first chlorine with the phosphorus. That's our second bond. That's the third bond, fourth bond, and the fifth bond of phosphorus with the fifth chlorine. Now let's count the number of valence electron for all the chlorine atoms after the formation of one bond with phosphorus. Now let's count for the first chlorine. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. That means first chlorine has attained octet, that is 8 electron in its outermost shell after the formation of one bond with phosphorus. Now let's count the number of valence electron for the second chlorine. The first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. That means second chlorine has also attained octet after the formation of one bond with phosphorus. Now let's count the number of valence electron for the third chlorine after the formation of bond. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means third chlorine has also attained octet, that is 8 electron in its outermost shell after the formation of one bond with phosphorus. Now let's count the number of valence electron for the fourth chlorine. That's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So the fourth chlorine has also attained octet after the formation of one bond with phosphorus. Now let's finally count the number of valence electron for the fifth chlorine after the formation of bond. So that's the first chlorine, first electron, the second electron, the third, the fourth, the fifth, sixth, seventh, and the eighth. So that means fifth chlorine has also attained octet, that is 8 electrons in its outermost shell after the formation of one bond with phosphorus. Now, let's count the number of valence electrons for the phosphorus after the formation of 5 bonds with the 5 chlorines. So that's first electron, second electron, third electron, fourth electron, fifth, sixth, seventh, eighth, ninth, and the 10th. That means phosphorus has attained 10 electrons in its valence shell after the formation of 1-1 bond with the 5 chlorine atoms. That means here the expansion of octet. That means phosphorus is having more than 8 electrons, that is 10 electrons in its outermost shell. Why phosphorus is doing so? Because phosphorus is available with vacant d orbitals in its third shell. So now let's understand this topic in hybridization. There I will give you reason why phosphorus is expanding its octet. Now, phosphorus. What's the atomic number of phosphorus? That's 15. What will be the valence shell electronic configuration in terms of subshells and the orbitals? That will be 3s2, 3p3, and the vacant 3d subshell with 0 electrons. That's the vacant subshell or the 5 orbitals of the 3d. Now, let's talk about 3s first. The 3s subshell will have 1 orbital. Now let's talk about 3p. The 3p subshell has 3 degenerate orbitals, that is orbitals with equal energies. Now let's talk about 3d subshell. 3d subshell will have 5 degenerate orbitals, that is orbitals with equal energies. Now let's fill the electrons. The 3s is having 2 electrons. The 3s is having 2 electrons. So that means we are going to fill 2 electrons in the 1 orbital of 3s. That's the first electron with a spin of plus 1 by 2. And that's the second electron with the spin of minus 1 by 2. Now, let's talk about 3p. The 3p is having 3 electrons. So we are going to fill the 3 electrons in 3p subshell according to the Hund's rule. That is, firstly, all the degenerate orbitals of 3p will get 1 electron each. After that, pairing will start. Here we are available with 3 electrons that we have to fill in the 3p subshell. So that's the first electron, the second electron, and the third electron. So this is called the ground state of the phosphorus. So that's the ground state of phosphorus. Now, let's come to the Lewis structure. Here, how many covalent bonds does phosphorus is forming with chlorine? It's 5 covalent bonds. All bonds are the single bonds between the phosphorus and chlorines. So all bonds will be sigma bonds. That means 5 sigma bonds are there. So as phosphorus is forming 5 sigma bonds, that means in phosphorus there must be 5 atomic orbitals containing 1 electron each, so that 5 orbitals of phosphorus will overlap with the orbitals of the chlorine for the formation of the sigma bond. So that means here must be presence of 5 atomic orbitals containing 1 electron each. So that means here in this case, the 1 electron from the 3s will excite to the orbital of the 3d. So here the electron has been excited and we are going to make the excited state now. First of all, that's our 3s. That's our 3p. And that's our 3d. Now, here one of the electron has been excited from 3s to the 3d. So here 3s is having only one electron now. Now 3p is having 3 electrons, the first, the second and the third, and one electron has been excited to 3d. So in 3d we are going to have one electron. So that's called the excited state of the phosphorus. That's the excited state. Now you can easily observe that in case of phosphorus we got the 5 orbitals, the one in 3s, the 3 in 3p and the one in 3d. We got the 5 orbitals containing one electron each. So now phosphorus is eligible to overlap with the atomic orbitals of oxygen for the formation of sigma bonds. Total of 5 sigma bonds, as there are availability of 5 atomic orbitals in phosphorus having one electron each. So now from this step, as all were the sigma bonds, in this case all were the sigma bonds, so that means here from this step intermixing of atomic orbital will start. Now during the intermixing, one of the s orbital, 3 of the p orbital and one of the d orbital will intermix to form 5 new hybrid orbitals. So I am writing one of the s orbitals, the 3 p orbitals and one d orbital. They will intermix, and this intermixing of atomic orbitals is called hybridization. So here in total 5 orbitals are intermixing, the 1s, the 3p and the 1d. So we will get the 5 new hybrid cum degenerate orbitals. So we will get 5 new hybrid cum degenerate orbitals. That means all the new 5 hybrid orbitals will have equal energies. So let's make that 5 new hybrid orbitals. Now, what will be the name of the hybrid orbitals? It's the mixing of 1s, 3p and 1d. So the hybrid orbital will be named as sp3d hybrid orbital, containing 20% s character plus 60% p character plus 20% d character per hybrid orbital. So that's the hybridization, and the name of the hybrid orbital is sp3d. The name of the another hybrid orbital will also be sp3d. So in total we got total of 5 new hybrid orbitals which will be named as sp3 hybrid orbitals. So we got 5 new hybrid orbitals, that's sp3d hybrid orbitals. So that's the hybridization. So in total we were having the 5 electrons. Let's fill that 5 electrons in sp3d hybrid orbitals. That's the first electron, the second electron, the third electron, fourth electron and the fifth electron. So here we got the 5 new hybrid orbitals, that sp3d hybrid orbitals containing one electron each. So now phosphorus is eligible to form 5 sigma bonds with the 5 chlorine atoms. Now let's talk about the chlorine. Chlorine, what's the atomic number of chlorine? That's 17. So the configuration will be 3s2 3p 5. So that means, first of all, 3p is having 3 degenerate orbitals, and we need to fill 5 electrons over there according to the Hund's rule. So that's the first electron, second, third, fourth, and the fifth. So let's make these 3p orbitals of chlorine over here for the formation of bonds. So that's the 3p of first chlorine containing 5 electrons. So that's the first, second, third, fourth, and the fifth. Here what's going to happen? In chlorine, we are having one of the 3p orbital which is having one electron, which is going to have head-on overlap with the sp3d hybrid orbital of phosphorus for the formation of the sigma bond. So this sigma bond is sigma sp3d p. Why so? Because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of phosphorus with the p orbital of the chlorine. Now let's talk about the second chlorine now. That's the 3p of second chlorine atom, which is having 5 electrons. Let's fill these 5 electrons. The first electron, second electron, third electron, fourth electron, and the fifth electron. And here we are left with the one atomic orbital which is having one electron, and this atomic orbital, the p orbital of chlorine containing one electron, will have the head-on overlap with the sp3d hybrid orbital of phosphorus for the formation of sigma bond. And we got the second sigma bond, which is named as sigma sp3d p. Why so? Because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of phosphorus with the p orbital of chlorine. Now let's talk about the third chlorine. This is the 3p of third chlorine. 3p of third chlorine, which is having 5 electrons. So that's the first electron, second, third, fourth, and the fifth. Now here we are left with the one atomic orbital in 3p which is having one electron, which is going to have the head-on overlap with the sp3d hybrid orbital of the phosphorus for the formation of the sigma bond. So we got the third sigma bond, that's sigma sp3d p. Why so? Because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of phosphorus with the p orbital of the third chlorine. Now let's talk about the fourth chlorine. That's the 3p of fourth chlorine. 3p of fourth chlorine. Now it's again having 5 electrons. So that's the first electron, second electron, third electron, fourth electron, and the fifth electron. Here also we are left with the one atomic orbital in 3p which is having one electron, and this atomic orbital is going to have head-on overlap with the sp3d hybrid orbital of the phosphorus for the formation of the sigma bond. So that's the sigma bond sp3d p, because this sigma bond has been formed by head-on overlap of sp3d hybrid orbital of phosphorus with the p orbital of the chlorine. Now let's talk about the last chlorine atom. That's the fifth one. This is the 3p of fifth chlorine. 3p of fifth chlorine. Now here also the 3p is having 5 electrons. So that's the first electron, second electron, third electron, fourth electron, and the fifth electron. Here we are also having again one atomic orbital which is having one electron, which is going to have the head-on overlap with the sp3d hybrid orbital of the phosphorus for the formation of the sigma bond, and that sigma bond will be sigma sp3d p. So because this has been formed by head-on overlap of sp3d hybrid orbital of phosphorus with the p orbital of the chlorine. So that's all about the hybridization of PCl5. Now let's talk about the structure. The hybridization came out to be sp3d. All were the sigma bonds, so the standard structure for sp3d hybridization is trigonal bipyramidal. Trigonal bipyramidal. Now let's make the structure. That's the phosphorus. This is one bond, the sigma bond with chlorine. This is another sigma bond with the chlorine, and this is the third sigma bond with the chlorine. Now this is the planar structure. I'm just hypothetically linking the chlorine atoms. These are not the bonds. This is just the hypothetical representation of the dash bonds to make you understand this structure in 3 dimensions. And that's the one bond with another chlorine over here, and that's the another bond over here with the fifth chlorine. Now, first of all, here the bonds which are present on the equatorial positions are called the equatorial bond. These bonds are called equatorial bond. So we are having total of 3 equatorial bonds. I am marking equatorial bonds to be EB, equatorial bond, and that's the also equatorial bond. Now, on the other hand, we are having the another 2 chlorine atoms with a bond called axial bonds. These 2 bonds are called axial bonds, the upper bond and the lower bond. Upper above the equatorial plate and the lower bond that's below the equatorial plate. So these 2 bonds with the yellow one are called the axial bonds. Now, one fact about this structure. The bond length of axial bond is greater than the equatorial bond, which will affect the strength. And what will be that effect? That axial bonds, due to the higher bond length, will be weaker than the equatorial bond. So that's all about this structure. This structure is named as trigonal bipyramidal. Now let's come to the last points, that's of energy. So here in this hybridization process, there is a consumption of 2 types of energies. The first one, here is the consumption of energy for promoting the electron from 3s to the 3d. So here I am writing consumption of energy for promotion of electron. So that's what will be called as consumption of promotional energy. That is the energy required for the promotion of electron from 3s subshell to the 3d subshell. And another energy required is the intermixing of the atomic orbital. I am writing here's the energy required is the consumption of energy for the intermixing of atomic orbitals, or we can say here is the consumption of hybridization energy. What is hybridization? The intermixing of atomic orbitals. So we got here the consumption of hybridization energy. Now here is the formation of the 5 sigma bonds with the hybrid orbitals of the phosphorus and the atomic orbitals of the chlorine. So during the formation of these 5 new sigma bonds, there is a release of energy. I am writing during the formation of 5 new sigma bonds between hybrid orbitals of phosphorus and atomic orbitals of chlorine comma, there will be release of energy. There will be liberation or release. I'm writing liberation. There will be the liberation of energy which compensates promotional energy as well as hybridization energy. That's why the formation of phosphorus pentachloride, that's PCl5, is practically visible. So that's all about the sp3d hybridization with the help of an example of phosphorus pentachloride. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on the thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.